Alright, no, you can ask questions, that's fine. So let's look at a couple of examples. We already did the stoichiometry. That's when we knew exactly how much of each reactants we need in order to get the amount of product that we're gonna need. Now, let's look at examples when your reactants are not in a stoichiometric ratio. So we want to make a Mickey Mouse, just a head. Alright? So, these are going to be the ears, and those are the heads. How many ears do we need for each head? Two of them, very good. So looking at the number of ears given to you and the number of heads, how many functional Mickey Mouse do you think we can make?
Four.
Four of them. Very good. Now, if you make four of these, you're gonna end up with 2 ears. All the heads are used, but you're gonna end up with 2 ears that are left over. So obviously we can't make another Mickey Mouse just because we don't have a head. So in this reaction, after assuming that this is a reaction, after it's done, you're gonna end up with 2 leftover ears. Or you call that excess of ears. And then the head, in this process experiment, the heads, we call them limiting. Why do I call this limiting? Because the number of Mickey Mouse heads that I can make is limited by the number of heads we have. In other words, we will stop making Mickey Mouse as soon as you run out of heads. So heads, or the number of heads that was given to you, is limiting the number of Mickey Mouse that you can make. So in this process, you call the heads as limiting because that's limiting the process of making Mickeys, and the ears are going to be the excess. Now, why do I call this limiting and excess? These 2 are my reactants, if you look at it as a reaction. So ears are going to be your excess reactant, and head is going to be your limiting reactant. So when we talk about limiting excess, it's all about your reactants. Now, what's important here is that the number of, or the amount, the number of products that you're gonna get depends, and it's controlled by your limiting reactant. Now, in actual reactions, when we talk about limiting excess, we're talking about molar ratio. You want to look at the balanced reaction and see if you have a stoichiometric amount of your reactants or not. If you have a stoichiometric amount, at the end, you're not going to have any leftovers of any reactants. But if one of your reactants is in excess, the other one is the limiting, at the end you're going to have some leftover, meaning that in your reactions you're going to have the product and some leftover reactant. So in your reaction vessel, reaction flask, you're not going to have just the products. Now let's do a couple of examples. I'll show you how we use this for chemical reactions. So I think the projector is tilted up a little. So let's do this. I'm gonna bring this. See if I can. Alright. So you're looking at a reaction of aluminum and hydrochloric acid. So aluminum metal reacts with hydrochloric acid, and from that reaction, aluminum chloride and hydrogen gas is produced. So to make sure this is balanced, you're going to need 2 aluminums and 6 hydrochloric acid. you want to know if you start with 20 grams of aluminum and 50 grams of hydrochloric acid, you want to know how much hydrogen gas would be produced. So, in a flask, I combine 20 grams of aluminum with 50 grams of hydrochloric acid. And I want to know how much of hydrogen gas would be produced, or the maximum amount of hydrogen gas that can be produced from the reaction of 20 grams of aluminum with 50 grams of hydrochloric acid. Now, since both quantities of reactants are given to you, in this reaction you have two reactants, aluminum and hydrochloric acid, and for both of them the initial quantities are given to us. The first thing you want to do is to check and see if these two quantities are in a stoichiometric ratio or not. Now, obviously, by just looking at mass, I can't tell if they have the proper ratio or not. I'm going to convert this to moles, and then based on the balanced reaction, I want to see if these two have the correct stoichiometric ratio or not. So the reason I'm doing this is because the initial quantities of both reactants are given to me. They are in grams, and I don't know if they actually have this appropriate molar ratio or not. So we have to check. If they have the appropriate molar ratio, then I can use either aluminum or hydrochloric acid to find the amount of hydrogen. But if they don't, if they're not in a stoichiometric ratio, I gotta see which one is limiting, which one is excess, and from there figure out how much product would be produced. So my first step now is to find out if these two, 20 grams of aluminum and 50 grams of hydrochloric acid, are in a stoichiometric ratio or not. There are a couple of ways, at least two ways, that I want to show you in order to find out if these two are in a stoichiometric ratio or not. Method one would be looking at the amount of product that would be produced. Like, I would assume that 20 grams of aluminum consumes completely, and I want to know how much hydrogen gas would be produced. So I assume all 20 grams of aluminum is consumed, and I want to see how much hydrogen gas would be produced. So I will convert from mass of aluminum to moles of aluminum, then I find the moles of hydrogen. And then I would assume in a separate calculation that all of the hydrochloric acid, all 50 grams, is consumed. And I'm going to find the quantity, either in moles or grams of hydrogen gas that would be produced. Now, what do we expect to see here? If these two, that 20 gram and 50 grams, are in a stoichiometric ratio, meaning that they have the proper mole-to-mole ratio, you would expect to end up with the same quantity of hydrogen gas at the end here. Remember the problem we did with sodium and hydrogen gas earlier? How regardless of which one you use, you would end up with 0.1 grams of sodium hydride. Same thing here. If these two end up giving you the same amount of hydrogen gas, it means that aluminum and hydrochloric acid are in a stoichiometric ratio. If they don't, that tells us that one of them is limiting, one of them is excess. So let's find out how much of hydrogen gas we can get, assuming that all the aluminum is consumed, and how much of hydrogen gas would be produced, assuming all the hydrochloric acid is consumed. And from there, we decide if they are in a stoichiometric ratio or not. So how about you all try with me? Start with 20 grams of aluminum and tell me how much hydrogen gas you would expect to get. Starting from 50 grams of hydrochloric acid, you want to find out how much of hydrogen gas would be produced. So I'm going to do this while you're working on it too. This is our solution map.
Why is it 6 moles of aluminum? I thought it was just 2.
It is 2.
Would it be wrong if we converted it to grams?
No, it won't matter. It's the quantity that matters. You can either leave it at moles or you can convert it to grams. Yes?
Is it, like, do we have to do sig figs for this calculation? Is it okay?
I did sig figs, but it won't make a big difference here. No. Because just we're trying to figure out if it's limiting or excess. But if I was asking for the amount of hydrogen, then you would want to do that. So, watch me here. Assuming that 20 grams of aluminum reacts completely with hydrochloric acid, I would expect to get 1.11 moles of hydrogen gas. Now, assuming 50 grams of hydrochloric acid reacts completely with aluminum, I would expect to get 0.686 moles of hydrogen gas. Now, how do I interpret this? Just the fact that I'm not getting the same amount, it could be moles or grams, of hydrogen gas, this tells me that there is a limiting excess reactant here. I call it situation. There is a limiting excess situation here. It means that aluminum and hydrochloric acid are not given to me in a stoichiometric ratio. Now, the next step is to find out which one is limiting, which one is the excess reactant. So the reactant that gives you the fewest amount or the least amount of product is going to be your limiting reactant. So from here, since hydrochloric acid is giving you less hydrogen gas, hydrochloric acid is your limiting reactant. And since hydrochloric acid is limiting, it means that aluminum is in excess. So by doing this, I found out that first of all, aluminum and hydrochloric acid are not in a stoichiometric ratio the way they're given to me. And based on the amount of hydrogen gas produced, I can tell that hydrochloric acid is my limiting reactant. What does that mean? It means that as soon as you run out of this hydrochloric acid, as soon as you use 50 grams of hydrochloric acid, your reaction is going to stop. Now, maximum amount of hydrogen gas that can be produced is controlled or limited by your limiting reactant. So the maximum amount of hydrogen gas that you can be produced is going to be 0.686 moles. So this is the maximum amount of hydrogen gas that's produced. Or what's the yield of hydrogen gas? 0.686 moles. Now this is in moles. If I ask you for the grams, for the mass of hydrogen gas or the maximum amount of hydrogen gas that can be produced, you multiply this by the molar mass of hydrogen gas to tell me what the mass of hydrogen gas is going to be. Now, in the test, if I give you this question, you can't box both answers for me. If you box both answers to me, it means that you don't really understand what limiting excess is. And there is no way I can have two different amounts of hydrogen gas produced. If you don't box anything, again, we don't know what the answer is. So you do your calculations. Once you do your calculation, you define which one is limiting, which one is excess, and then you want to tell me that based on your limiting excess reactant, the maximum amount of hydrogen gas is going to be this one, or the yield of hydrogen gas is going to be 0.686 moles. The common mistakes that students do on this type of problems, first of all, not checking for limiting excess at all. They randomly pick either aluminum and hydrochloric acid, and they just found it. Sometimes they're lucky, they pick the right one, but that doesn't show you understand the limiting excess. That's one thing. Or they don't box the right answer, or they box both of them. So make sure that after you do this calculation, you either box or you write a line and tell me that, since this is my limiting reactant, this is the maximum amount of hydrogen gas that I would expect to get. Questions? So 0.686 moles of hydrogen, that's the maximum amount of hydrogen gas produced. That's the yield for your hydrogen gas. Or we also call this a theoretical yield of hydrogen gas. Why do I call this theoretical? It means that theoretically, using 20 grams of aluminum, 50 grams of hydrochloric acid, based on this reaction and calculations, I would expect to get 0.686 moles of hydrogen gas. Or this is the expected amount of hydrogen gas. These are all the different words, phrases, terms that you're going to hear in this type of questions. Any questions so far? So now, what does this mean? Like after doing all these calculations, what it means is that if I have a flask and I put 20 grams of aluminum in there and I add 50 grams of hydrochloric acid to this solution, to this aluminum, let's say we add this, these two are going to react with each other. After they react, what would you expect to see in your flask? Yes?
A smaller amount of aluminum.
Very good. So I would expect to see excess aluminum because not all the aluminum is going to react. So we would expect to see excess aluminum metal. What else do I see here in the flask? Hydrogen gas, that's good. So you would expect to see 0.686 moles of hydrogen gas. What else?
The other product of the equation.
Very good. The other product, I would expect to see aluminum chloride in here too. How would you find the amount of aluminum chloride in here?
You would have to do a stoichiometry for aluminum chloride as well, the way we figured out for hydrogen.
Very good. Which reactant do I use for this? Aluminum or hydrochloric acid?
You would use the limiting reagent.
Limiting reactant, you're gonna start, very good, with 50 grams of hydrochloric acid. You do mole to mole ratio to figure out how much aluminum chloride would be produced. So why don't you guys do that? Assume that you have 50 grams, not assume, you have 50 grams of hydrochloric acid, and hydrochloric acid is your limiting reactant. Find out how much aluminum chloride would be produced.
In moles or in grams?
Let's do moles, since we're doing everything in moles for now. Put the eraser. Do you see the eraser? There. So I convert first to moles, and then based on the balance reaction, each 6 moles of hydrochloric acid gives you 2 moles of aluminum chloride. So by doing this calculation, I found out the maximum amount or the theoretical yield of aluminum chloride as well. Aluminum chloride is one of our products. So now look at this. Now I have a better understanding of exactly what I have in my reaction flask. I know exactly how much hydrogen gas, I know exactly how much of aluminum chloride solution is going to be there, and I know that there is going to be some excess aluminum. Now let's see how much excess aluminum we're gonna have here. We wanna find the excess aluminum or the leftover aluminum. So you want to find the mass of excess aluminum. Because the only part that I'm missing is the mass of excess aluminum. And once you know how much excess aluminum you have, you know exactly what you have in your reaction flask. So, in order to find the excess aluminum, our first step is to find out how much of the aluminum actually reacts with the hydrochloric acid. Once we find how much of it reacts, we can subtract that from the initial quantity of aluminum and find how much is left over. So to find the excess aluminum, our first step is to find out how much aluminum reacts with 50 grams of hydrochloric acid, or how much aluminum do I need in order to consume this 50 grams of hydrochloric acid completely. So how do I do this? From the mass of hydrochloric acid, I'm going to find moles of hydrochloric acid. Once I find moles of hydrochloric acid, I'm going to find moles of aluminum, and then I'm going to find mass of aluminum. This would give me the mass of aluminum metal needed for 50 grams of hydrochloric acid. And I do this because I already know which one is limiting, which one is excess. So let's do it. Hydrochloric acid, you have 50 grams of hydrochloric acid. Each mole hydrochloric acid is 36.46 grams of hydrochloric acid. So mass and mass cancel out. Based on the balanced reaction, each 6 moles of hydrochloric acid reacts with 2 moles of aluminum. And then we know that each mole aluminum is 26.98 grams. So from this equation and calculation, I find out that for 50 grams of hydrochloric acid, all I need is 12.3 grams of aluminum. So based on the stoichiometry, mole to mole ratio, I found out that all I need for 50 grams of hydrochloric acid is 12.3 grams of aluminum. Does this make sense so far?
Yes.
Now, all I need is 12.3 grams. But what I'm given is 20 grams. So we should be able to find the excess aluminum. So 20 grams, which is your initial amount of aluminum, you subtract that from 12.3 reacted. That gives you the excess aluminum, which is 7.7 grams. Now this is 7.7 grams excess aluminum, or you call this leftover aluminum, or you call it unreacted aluminum. Initial amount of aluminum. So since I knew hydrochloric acid was the limiting, aluminum was excess, I found out the mass of aluminum that's needed for 50 grams of hydrochloric acid. By doing this calculation, I found out that only 12.3 grams of aluminum is needed for 50 grams of hydrochloric acid. Now, I started with 20 grams of aluminum. All I needed was 12.3 grams of aluminum. That would be the excess of aluminum, 7.7 grams. Now, what does that mean? If I go back to my chart here, yes, in this flask, I would expect to see 7.7 grams of aluminum as well. And this is just beautiful, isn't it? You just found out exactly, you identified the type of chemicals and the quantities of each one of them in your reaction mixture. I think this is amazing. Now, how does this look like? What it looks like is that after it's done, I would expect to see a clear, colorless solution in my flask. On the bottom, there is some shiny metal. That shiny metal is going to be aluminum. That clear, colorless solution is the aluminum chloride solution. And over here, you have the hydrogen gas. Obviously, you won't see it, but it's inside your beaker or your flask. Now we have a better understanding of what's happening inside a reaction flask. Now, if I see a little bit of chunk on the bottom of this beaker, it's not unexpected. I know that based on what I did, there is excess aluminum here. I'm not going to assume that's just aluminum chloride or something went wrong or anything. Now I know exactly that's what I expect to get in my flask. Yes?
What is this reaction called?
It is a single displacement reaction.